Hi everybody, welcome back to another episode of Engsci Recap. My name is Jason. I just finished my second year of engineering science at the University of Toronto, and today I will be continuing this series with my second year classes. So this is the first video I'm recording um, for second year, and we're going to start off with this class, AER210, Vector Calculus and Fluid Mechanics. So as I said, this is the second year course I took in my fall term in engineering science, and uh, the instructor I had was Professor Alice Ekmekci. And so this course, as suggested by the name, was split into two parts. Vector calculus was the first half, and fluid mechanics was the second half. So in the vector calculus half, we began by learning about double and triple integrals, polar, cylindrical, and spherical coordinates. And then we learned about applications of iterated integrals, so mass, center of mass, centroid, moment of inertia. We learned about the Jacobians, so change of variables. Learned about line integrals, Green's theorem, surface integrals, divergence and curl, the divergence theorem, Stokes' theorem. And in the second half of the class, in the fluid mechanics section, we started off by learning about hydrostatics. Then we learned about different instruments for measuring pressure, buoyancy and stability, fluids in linear rigid body motion, in rotational rigid body motion. We learned about the Bernoulli equation, Reynolds transport theorem, the continuity equation, the momentum equation, as well as some open channel flow, and a little bit about compressible flow. So the question that I'll be going over today is from Midterm Test 1. It's question 4, and I took this test on October 28th of 2021. And the topics this question covers include the line integral over a vector field and the line integral over a closed loop. And in fact, part of this question is very specifically testing Green's theorem. So this is the statement of the question. It's split into two separate parts, both of them involving line integrals. So as you can see in the first part, we have a line integral. We have a line integral over a vector field. So we're given the vector field capital F, and the curve C that we're integrating over is given parametrically with parameter t, and we're given that t is between -1 and 1. And so we just want to evaluate the line integral f dot dr. So this is simple enough. And in the second part of the question, this is completely unrelated to the first part. We're asked to evaluate this line integral, but we're asked to use Green's theorem, and C is given to be a closed loop defined by a rectangle with vertices 0, 0, 1, 0, 1 pi, and 0 pi. So as you can see, the differences in these two questions, obviously in the first one we have a vector field and it's an open loop, whereas in the second part of the question we have a closed loop and we don't have any vectors involved. So we'll do the first part of the question. So we'll evaluate the line integral f dot dr over the curve C, and we'll call this the answer I. So we can rewrite the expression f dot dr by noticing that the dr vector is going to be the equivalent of r prime of t multiplied by dt. The reason for this is that the derivative of our parametric curve is going to be tangent to it. So we can also rewrite everything in terms of the variable t. We no longer have a dr, but we have a dt, which means that we can insert the upper and lower bounds for t, which are -1 and 1. So -1 is the lower bound and 1 is the upper bound. And we should also notice that f will take in r of t, because r of t will be a position and f is the vector field. So in order to find our expression for f of r of t, all we have to do is plug in r of t into the x, y, z components of f, and we find that the vector will be equal to this, 2t, t squared, 3t. And to evaluate r prime of t, all we have to do is take r of t and take the derivative with respect to time of, or with respect to t, I should say, of each vector component. So we have these two expressions, and what we can do is we can then plug them in, take the dot product, and we should find that our integral I is equal to this. We can simplify the integrand even further, and noticing that everything in the integrand is in terms of t, we can simply integrate this expression, plug in our bounds, and we find that the integral is equal to -2. So that is our final answer. For the second part of the question, we're asked to evaluate this closed line integral using Green's theorem. So we should notice immediately that inside of our integrand, we have a dx, a term multiplied by dx, and a term multiplied by dy. And this should remind us instantly of Green's theorem, because given this closed loop integral, we can relate this closed loop integral to a integral over a 2D surface using Green's theorem. So this is a statement of Green's theorem. The closed loop integral of p dx plus q dy is equal to the 2D surface integral over the region R that's enclosed by C of dq by dx, or I should say del q by del x minus del p by del y, as I said, over the region R. And the relationship between C and R is that R is the region bounded by the closed loop C. So this is a very important result in vector calculus. And we should notice that in order to find q and y, all we can do is just equate the expressions in the original integrand corresponding to p and q. So p in our case is the term multiplying dx, which is e to the x cosine y, and q is the term multiplying dy, which is e to the x sine y. So we can rewrite our integral by using Green's theorem, replacing the closed loop integral with the 2D surface integral. And we take the partial derivatives with respect to x and with respect to y of q and p respectively, and we subtract them. So taking the partial derivative of the first term, there is no difference because sine y is simply a constant and e to the x does not change when we take the derivative. And the second term, when we take the partial derivative with respect to y, we get a minus sine y, so the negative signs will cancel out in the end, and our integrand will simply be 2 e to the x sine y. And now we need to figure out what exactly we're integrating over. So what is the 2D surface in the xy plane that we're integrating over? Well, if you'll recall, in the question we're given 4 vertices, and those vertices are of a rectangle. And the original closed loop integral was meant to integrate over this loop. However, since we're using Green's theorem, all we care about is the region inside this loop that's bound by the curve. And this is labeled R in this diagram. Please excuse the rather messy drawing. But if you recall, the 4 points we were given were 0, 0, 1, 0, 0 pi, and 1 pi. And so that's represented in this 2D Cartesian plane, the xy plane. And so this is rather simple to translate into bounds. We just our dA will be dx dy, and the region R will have, so y will have the bounds 0 and pi, and x will have the bounds 0 and 1. So as you can see, this is what our integral simplifies to. We replace the dA with dx dy. X goes from 0 to 1, y goes from 0 to pi. And this is rather simple to evaluate. We can split up the iterated integrals because we have a product. And I guess this dy should, in fact, you could move this dy into the first integral as well, and that would be equivalent. So we perform the rather simple integration of e to the x, and we integrate sine y as well, which will just give us minus cos y. And this is all rather just pretty basic integration, but at the end of the day, our final answer will be 4 times e minus 1. So that's the end of the question. And before I end off this video, I'd like to make some quick acknowledgements. So I'd like to thank Professor Ekmekci for the course and the midterm test content. I'd also like to thank my tutorial TA, Rahul, as well as the individuals who made this Beamer template. So yeah, I hope you enjoyed learning about AER210, and I hope to see you in the next video. Take care.